doing this in parallel, or you wait until the first reaches the 2 and then you run the next one?
No, it's going to be completely in parallel. So the intuition here is that I take my initial 1 unit of capital, I give a half to the first guy, which will be at level 2, then a quarter to 4, and an eighth to 8. And then each of these strategies gets a tiny amount of money, and they have a threshold in mind, and they start playing like our original P until they hit the threshold and they stop. And well, what we want to happen is that if all of them stop and get to their level, then they multiply their initial capital exactly by so much that they now have 1 each. But I'm confused because I seem to get another 2 to the minus k. Let's see if that's true. So how much do you have if you play from 2 to the minus k? Oh no, that's alright. Okay. So yeah. So this is what Q will get if you start from 1. It will be the scaled down version, because you allocate a fraction of what each of these guys get when you play them in isolation. And so now if you're in case 2, then there will be higher and higher capitals around. If that happens, each of those P's with a cutoff threshold will get to their threshold and pay out that level, but you did scale their allocated capital down, but it's still enough. So if P gets you infinitely rich, then will be sum of 2 to the minus k times 2 to the k. And it may be actually more. Is that okay so far? So this is the first tool. It's sort of nice. It says, don't worry about getting the capital all the way up. Just make sure it gets big. And then it can go down again, but it has to then get bigger. Alright. So now let's do the second one. If skeptic can weakly force E1, E2, etc. So a countable list of events. Then we can also force the intersection. Says if one thing should happen, or you get infinitely rich, and another thing should also happen, but you have a separate strategy that gets you infinitely rich there, and a third thing, you have a strategy for that, and you have one strategy that makes sure that either they all happen, or you get infinitely rich. Right? So we want to make a single master strategy that whenever one of them fails, the master strategy already has enough leverage from all of them to get infinitely rich itself. Good. But here it's going to be even easier, because infinite is so big that if you scale it down a little bit, it's still infinite. So we're going to just look at all the strategies that are witnesses for this weak forcing. And we're going to do something pretty well, good enough, so it works. You just say, okay, let's play a little bit of all of them. So again, I take my initial capital of 1, I split it in countably many pieces, I give a small chunk to strategy K, and then if strategy K makes the small chunk, would have made 1 into infinity, it will still make the small chunk into infinity. So now if you have the capital Q, this, then if any K goes to infinity, so let's be a little more specific. If the supremum of one of them goes to infinity, that's weak forcing, then plus KQ also goes to infinity. Yeah, so here it's important that strategies cannot end up with a negative capital, because then there could be cancellations. One of them gets rich, the other one gets negative, and you don't know what you can conclude. But because all of them have to never go bankrupt while doing their forcing, we're only summing up a positive thing. So 1 infinity closes it out. I'm doing sort of hopefully all the intuition and most of the construction and almost none of the proof, as you can see. But I don't think this is sort of the thing I want to really focus on for this lecture. And if you sort of need to see, this is sort of very well written in the chapter 3. But I think the constructions are quite intuitive. So now I want to get to the strategy for the law of the large numbers. And we're going to make a countable list of them. One achieving sort of almost what we, so every one of them achieving closer and closer bounds on this statement. And then in the end we say, okay, let's weakly force all of them, and then boost it to forcing, and then we have the theorem here. Okay. So what we're going to show is that if you fix some positive epsilon, then you can force that the limit superior. Is the picture still there? No. So let's do it again. So we were worried about these sequences that have averages that keep on bouncing. What we're going to do is we're going to make sure that the limit superior, that's the limit of the peaks in some sense, but that cannot be large. And then we have a symmetric thing to say the values have to be high, and we still allow some small wiggle room, but we can do it for every possible size of the band in which we squeeze everything. And then we use the weak forcing of all of them together, and then we have fixed it to be, they have to converge to a half. Okay, so we're now going to look at one of these events. We're going to fix an epsilon, and we're going to say the limit superior cannot be big. Good. So it has to be at most epsilon. So that means that if you look at this epsilon level, then here is 0. What is still okay with this is if you take a while to get under this epsilon, but then you forever have to stay under it. So you can still do nasty stuff below, but we're going to use the symmetric version to say that that can also not happen. But you definitely cannot infinitely go above epsilon. Okay, so how do we do it? So we want that we have to find a way to invest that gets us rich if these averages are often too high. Right? So too high probably means that we want to buy tickets, because buying is good when they are too high. So the first thing you could think of is to say, okay, let's just invest all our money in buying, why not? Right? That gets us the richest if it's high all the time. But the problem is that one negative outcome makes you end up at 0. So that's not good enough. So we cannot just invest everything. So we invest a small amount, but we still have the effect that that small amount, just by the occurrence of too many high things, will get us larger and larger gains. So let's see how that works. So the idea is that we start at 1. So now I'm going to switch to the protocol way of defining the k. We start at k equals 1, and we're going to play mn equals, so that's how many tickets we buy, and we're going to invest a small fraction of our capital in tickets, in positive amount. Right, so we have a certain amount of money, we take an epsilon fraction of it and buy tickets for x. So if x is too high, or if it comes out high, then we gain. If it comes out small, we lose. So the first thing you can see is that because we're always investing a fraction, we're never going to go negative. Because we lose a certain fraction, but that's okay. That cannot bring it across 0. Alright, so now let's see that this strategy forces this. Right, so what does forcing mean? Well, we only have to weakly force it in this case. Weakly force means that either this happens or we go infinitely rich. Okay. So let's turn it around. If our capital stays finite, this better happen. That's the converse. So we're going to show that if the capital stays finite, this happens. Good. So what is our capital? So if you look at it, you see that Kn is going to be Kn minus 1 plus Mn xn. It's going to be Kn minus 1 plus Kn minus 1 epsilon xn. It's going to be what it was times 1 plus epsilon xn. And that means, if you roll this out all the way to the beginning, that it's going to be a product of the form 1 plus epsilon xi. Yeah, so our capital will be a product of factors, and if the x was positive, they help us. If the x was negative, they hurt us. Okay. Last bit, and then we'll do the break. So the goal is now to show that if the capital never gets arbitrarily big, then let's call this something. This event happens. We can show that, and if it doesn't happen, we get infinity rich. That's what we wanted. Okay, so say that Kn is bounded by some constant. If its supremum is smaller than infinity, you can find a number such that it's always below. That is all n. Alright. So we look at what the capital is, and at this point it's nice to take a logarithm because then the things start to sum. Then we get that the log of that, which will be the sum of the logs, this is the log of the capital, it's going to be smaller than the log of c. And now we want to work towards having this average appear. And the idea here is that epsilon is going to be very small, right? We don't really care about the large ones. We care about the very small ones because they are squeezing this thing the most. So we want to do something to make this intelligible that is pretty good for small epsilon. And the trick here is to use that log, say 1 plus some number, is more than this number minus the number squared. If it's not too small. Yeah, so if you do a Taylor expansion, then you actually get a lower bound of t. So this says you need a correction. You get an upper bound of t on this. This says that you can also get a lower bound by subtracting something. And in case that this t was small, the subtraction is sort of not really big. It's the square, so it's good enough. So we're going to use this. So we're going to make this even smaller. And we're going to find that the epsilon xi minus epsilon squared xi squared is less than some constant. So now we're almost there, because this starts to look like this average that we want to say something about. So if we divide by this epsilon and also divide by n, then we have the average here. Okay, so let's bring this to the other side. So we divide it by epsilon and n. Let's do epsilon because we divide by epsilon. Okay. And let's do one more little thing. Let's say we don't really care about the squares so much. How can we get rid of them? Well, let's just put the biggest value they can have. And because of the boundedness of the protocol, they're each at most 1. So this is, oh, I forgot to do that again. Okay, so they're each at most 1. So the average is 1. So that's just epsilon. Okay, so 2 more steps, then we're there. So the first step is to say, this whole derivation, it holds for all n. Okay. So that means that I can take the limit. So what's the limit of this? Well, that's what we want to find. What's the limit of log c over epsilon n? Of 0, because n makes it go. And what's the limit of epsilon? Just epsilon. Okay, that's good. So we now got here. So let's put it all together. We can force that it may not exist, so let's take it. The Lim soup is bounded by epsilon for each epsilon of our choice. Okay, so let's make an event for each epsilon on a discrete set of smaller and smaller ones. Then we can weakly force the union, which means that the Lim soup can be at most 0. Because that's where they all intersect. If you're smaller than any number, you're smaller than 0. And then we go through the weak to strong forcing to make a winning strategy. So that's a one-sided picture only. But it turns out that if you do the same argument with minus epsilon, everything still works, except you get a minus in the end result. So you find that the lim inf is larger than minus epsilon, and that gives you the symmetric squeezer from the other side. So if you then do both sides together, you get the final result that we want, which is this one. Okay, so that's what I wanted to say in the first half.
Could you put up the blackboard a bit?
Sorry?
Could you put up the blackboard a bit?
Yes.
Thanks.
So the one thing I wanted to say about it is that the strategy that we get right now is a little bit, how do you say it? It's not non-constructive, but it's ethereal, I'd say. Right? It goes through this sequence of building blocks. So you don't really have a good sense of what is the strategy that I got when you can unpeel everything and get there. So what I did is I put a sort of alternative, very concrete strategy in the homework so that you can play with that one instead. There's no infinite sequence of things simultaneously enforced. There's just one way to pick Mn, and it already gives it. All right, let's have a break.